This is Grep. It's a 50-year-old tool people use every day to search for strings in files. But I was wondering, how easy is it to make a fast version in modern C++, and how would that stack up against modern alternatives such as the Rust darling Grep? Before we start, let's address the large language model elephant in the room. All the C++ for this project was handcrafted artisanal code from a small English village. However, I did have a chat window up so I could ask the Oracle questions around Linux internals and why my CMake at various points in the project had the internal sadness. Now that that's out of the way, let's talk project setup. For this project I had 3 strict rules. It should use bleeding edge C++, so that's C++26 with a trunk build of GCC, fortune favours the brave. It should use modern C++ paradigms only, RAI, smart pointers, ranges, etc. It should be a self-contained standalone binary. The first 2 are easily solved with a Docker file, but the third requires a bit more thought. We're going to statically link everything, including libc. As this is notoriously difficult to do with GNU libc, we're going to sack that off in favour of Muscle, a standalone libc implementation designed for embedding. We can extend this self-contained idea even further though to bundle multiple tools in one executable. If we check the value of argv0 in main, then we get the name of the current executable. Thing is, Linux honours this with symlinks, so we can just build and deploy our app once and then create symlinks for each tool we want to support. This leads us to some fun modern C++ features we're using. Ranges to convert the raw C input args into a vector, and contracts to codify our pre and post conditions in the actual function signature. In addition to that, I'm also using an experimental C string view. In C++ we have std_string_view, which is a non-owning view over a string that is cheap to copy. Fun fact though, it's not guaranteed to be null terminated, so you cannot safely pass this into C APIs that expect null termination. CStringView is proposed for a new type that acts the same as stringView but guarantees the null byte. The paper is currently working its way through the standards committee, so I'm using the reference build, so we're potentially using C++29 features. Before grep, we should start small to prove out our architecture. Let's start with cat. Cat is a utility that reads a file and prints it to the screen. How hard can it be? It turns out way harder than you think if you care about bleeding edge performance, which I know you do because that's why you're here. Let's talk architecture. I want a pipeline system, so this means having something that produces data, a source, 0 or more transforms for the data, and then something that outputs the result, a sink. The aim here is that we can isolate each of these components and easily chop and change them as we need, with data always flowing from the source to the sink. Now, one of the great things about C++ is that it's multi-paradigm and quite unopinionated on how you structure your code. A fair starting point for this would be to define some sort of base class for the source, transform and sink, and then use runtime polymorphism to chain them together. This gives you full flexibility in your choice of components, as well as a strict and enforceable interface. But there's no such thing as a free lunch, and it's not without some drawbacks. However, I think people are often quick to dismiss runtime polymorphism as being slow for the wrong reasons. The way dynamic dispatch works is that the program has to do extra pointer dereferences to resolve the concrete function being called through an interface, which we can see here. On modern CPUs, I'd posit that this extra dereference has minimal impact on runtime performance. Where the impact does come in is how modern CPUs optimize for you. They have instruction caches and branch predictors, and these will improve performance when your application takes deterministic execution paths. So, if in a hot loop you're always dynamically dispatching to different types, then you'll be working against these optimizations. It also means the compiler cannot easily inline calls, i.e. embed functions directly at the call site to elide a branch. This isn't impossible to achieve with link time optimizations or careful use of devirtualization, but you're always fighting the happy path. For this project, I want to do all the component composition at compile time, using templates. There'll only be a fixed set of concrete types, and I'm not writing it as an extensible library, so I don't need the flexibility of OOP. Let me show you how this works. Look at this source type. It has a call operator defined, and this allows me to call the object like a function. But it's templated on the next type in the chain. This means that when I compile this function, it already knows what it's going to call next, so the compiler can fully optimize it. And if we look at the assembly here, we can see it inlining the next call rather than branching to it. So the compiler is able to take our entire pipeline and crush it down to effectively almost a single function call. But passing in template args to template args is a pain. What we want is a better composition model. So using a small amount of clever templating, we can overload the bitwise OR operator. This then allows us to compose components together with the pipe operator, and this is exactly how C++ ranges works. When this compiles, it will automatically resolve the types and allow each stage to know what it's passing data to. Right, cool, whatever. But how do we implement cat? We need a source, and that source is a file. I'm going to jump straight to what most people will pick first when optimizing reading, and that's mmap. This is a Linux syscall that directly maps a file into the address space of the running program and is often considered the fastest way to read a file. To prove out the pipeline infrastructure, I also added a transform node that does syntax highlighting, so this is now more similar to the excellent tool BAT. I use the tree sitter library for the syntax highlighting, and it's nicely self-contained in a transform component, and I can also use environment variables to control which pipeline is used. Ironically, for all the future tests, I will disable the highlighting to ensure it's comparable to GNU Cat, making all this tree sitter integration effort largely pointless. We all make mistakes. And the sync is just the classic std out, warts and all. And that works fine as a baseline implementation. But we want to be methodical in our approach, make single changes, measure, then improve. And for that we need rigor both in terms of tooling and our mentality. So let's roll out the tools we'll be using. Hyperfine, command line tool benchmarker, which handles a lot of nuance like file system caching. Perf, the profiling tool, which allows us to see what functions our program is spending its time in. And strace, the all reliable, break down which syscalls our program is making. In addition to that, my dev machine is WSL, which could have some peculiarities. So I'll be benchmarking everything on a fresh Ubuntu install on a 2-core VM on my home lab. This should be about as representative as the real world as possible. The first thing I want to do is verify if mmap is faster. Linus himself has said that if you're sequentially reading a file, then just a simple read syscall can be faster than mmap. We'll read into a large statically allocated and large page aligned buffer and then just yield chunks down our pipeline, which our architecture beautifully supports. I'm also using pread over read as it doesn't update the kernel file offset, so potentially slightly faster as we need to do that bookkeeping ourselves. Anyway, this means zero dynamic allocations, and for files under 10 megabytes, the size of our buffer should be a single syscall. I say should, let's be responsible engineers. The man page for read states that the call may return having read less than the number of bytes requested. This is not an error, it's just a curio of Linux, and we need to account for this. So we'll actually read in a loop and on each iteration try to get the remaining bytes that we want. Let's run our first benchmark of read versus mmap versus GNU Cat. mmap is over 2,000 times faster than our read call, which I find hard to believe given the research we've done. We've stepped into a bit of a bear trap here that exemplifies the difficulties of benchmarking. When you call mmap, it doesn't actually map in the file at the point of call, it just commits the requested space in the process. It's not until you try reading from the mapped file that you generate a page fault and the kernel goes and fetches that page of data for you. Because our test is read file and write to dev null, the file itself is never actually read, so it appears blindingly fast. A fairer test between mmap pread is to touch the first byte in each page to force the kernel to actually read the file. And now we can see mmap is definitely slower, so we can discard that. At this point I figured a quick win would be to remove std out, which does a lot under the hood like taking locks. We can mirror our source approach by using the write syscall, again writing in a loop to ensure nothing is lost. And there's no real gain in performance. If we strace both our implementation and cat, then we see something weird. Firstly, our implementation is dominated by read time, so whilst we improved writing, it's not the lion's share of the work, so it's marginal gains. Secondly, cat is cheating. Look here, instead of reading a file, it's calling splice. Cat knows it's writing to dev null, which is technically a special type of file, so it's using an optimized syscall called splice to copy data directly from one file to another, all in kernel space. So it's not paying the price of copying data to userland like we are. If cat is cheating, then so should we. We can query the type of output and create custom pipelines for these different optimized situations. My first thought is to use sendFile, which is another zero userland copy syscall but has a much more ergonomic API. So we wire that up to a new pipeline. And it's slower. I guess cat uses splice for a reason. Splice works on pipes, which are a Linux IPC mechanism. However, in certain situations, like reading from a file to dev null, we can construct pipes to act as a middleman between them. We need to tweak certain flags like the fsetpipes, but given that boilerplate, we can call splice when reading. And now we're pretty much neck and neck with cat, even issuing a similar number of syscalls. At this point, regardless of our architecture, we've removed almost all of the userland runtime and we're now just driving the kernel in an efficient way as possible. Exactly like cat does. Grep time. I want to focus on just a single use case as a vehicle for our optimization journey. This is not meant to be a fully featured replacement. Our test corpus will be 2 clones of the Linux source code, that's over 200,000 files and about 4 gigabytes of data. Again, I'm more interested in doing incremental improvements than necessarily building a fully featured tool. Our test case will be simple. Find all occurrences of the struct keyword using a regex. In vanilla grep, that looks like this. I will be trying to normalize the options and flags between the various tools to keep it fair. Our initial implementation is very naive and uses all the basic C++ primitives. We have a pipeline that uses std file system for directory traversal, into a mapped file, into a std regex matcher, into a std cout sync. Again, this is very much the embodiment of a first pass baseline a lot of people will reach for first. Std regex is particularly egregious here. The way it's spec'd in the standard leads to an incredibly poor performing implementation. It's often anecdotally cited that it's quicker to spin up a PHP interpreter and pass a regex than it is to use std regex. But this is the beauty of C++. It gives you a bunch of primitives out of the box, but you're free to replace them with specialized implementations as needed. Vanilla grep is nearly 70 times faster than our naive implementation. If we look at the perf results for our implementation, then we can see 59% of the time is spent doing regex depth first search, and 11% of the time is spent doing vector copying, so we've got a lot of memory churn. And on the long tail, we're burning cycles constructing std locale objects, so trying to respect some language settings. The obvious next step here is to replace the regex library, and for that I'm going to use vector scan. This is a highly efficient and SIMD accelerated regex matching library used in deep packet inspection applications. So we vendor that into our application and build a new transform component that uses this library and slot it right into our pipeline. And it's a massive improvement. Std regex really is the worst. 170 seconds down to 7. Now, looking at perf, our time is dominated by std file system. Vector scan is only 9% of the CPU time, so it's time to upgrade our file I/O. The end goal is probably I/O U-ring, so let's do that. I/O U-ring is a feature in modern Linux kernels that lets you queue up syscalls and have the kernel execute them in batches asynchronously. It boils down to 2 queues you share with the kernel, one for submissions and one for completions. Using the liburing library, you can push work to the submission queue and then wait on the completion queue. It's not a trivial API to use, and it doesn't really fit our pipeline architecture, so let's just build a new abstraction. Now we have an event loop class that allows a caller to push work into the I/O U-ring queue, and then we can then pump that until all the work is done. We can keep the compile time customization by templating the whole event loop on handlers. These are custom classes with call operators the event loop will call back into when it completes a syscall. And here we've got handlers for open and close. This idiom is called policy-based design. So we want to walk all the directories. Fine. My initial hope was to use the I/O U-ring get dense submission, but this option seems to have a bit of a tumultuous history in the Linux kernel, and it's not available on either my dev or benchmark machine. In fact, there's an issue in the liburing GitHub suggesting that it was removed from the kernel. Instead, the architecture will be maintain a separate queue for directory submissions, and then do a fast, synchronous directory iteration first, then handle the I/O U-ring submission. The first part is easy, just use a vector of objects representing the directory to enumerate. Then, at the start of the pump loop, we create an empty vector and swap that with the member version. This instantly grabs all the queued entities and resets the queue to 0, all in 3 pointer swaps. The fastest way to enumerate a directory is probably with the raw getDense64 syscall. The man page for this specifies there is no libc wrapper and that this is not the interface I am interested in. Instead, it directs you to the higher level readdir call, but I think we can handle a raw syscall. For this call, you give it a file handle to an open directory and a buffer. It then squirts data about each entry into that buffer. We need to call this in a loop in case the buffer we provided was too small, and again, we're using a static buffer to avoid dynamic allocation. Each entry tells us the name of the subentry, whether it's a file or directory, and the offset in bytes to the next entry. We then pass the result through to the user's getDense handler, which then either queues up an open file or another readdir operation. After a bit of faff, I managed to get it to work, and it can process 4 GB of files in about 3.3 seconds. But we can do better. We need to leverage all the threads we have. To do this, we need to change our architecture. One thread handles the I/O via I/O U-ring and getDense. This pushes read file data to a queue where the remaining threads pick these up, do the expensive regex handling, and then output it. So we should be able to parallelize the expensive bit. And the performance is actually worse. In the single-threaded version, we were just passing around non-owning spans to the data as we had a deterministic lifetime. But now with threads, we cannot guarantee that by the time a thread comes to process the read file data, that buffer hasn't been reused for another IO uring call. So whilst I was using std move to efficiently move the buffers around, I was still reallocating new buffers for the new IO uring calls, so inadvertently still spending a lot of time resetting and zeroing out buffers. It's also spending a lot of time in munmap, which we don't explicitly call. This will be coming from some malloc calls, as we're still allocating in the hot loop. Before we embark on a massive rewrite, a quick win would be simply to just use a better malloc. So let's grab memalloc, an efficient malloc implementation from Microsoft, and drop that in. Because we statically link everything in, all malloc calls will now use this new implementation. And look at that, 2 seconds gone, just from using a different malloc. We're still spending a lot of time doing memcopy. The muscle memcopy is deliberately very basic as its focus is on simplicity and small size, but we can replace that with a SIMD accelerated version from Diptyque, a fast packet filtering library. We don't need the entire library, just their memcopy implementation, which we need to fudge slightly to make it standalone. We see some improvements here, but the biggest issue is the fact that we're still doing memory allocations on the hot path. So we do another massive refactor. This time we keep the internal request objects alive and pass around pointers to those into the user supplied handles. This way, once a read call is finished, we don't have to touch its buffer again until it's been processed. This isn't a free change, there's a lot of complexity, and I have to manually handle the lifetimes of the requested objects. In addition to that, for directories with lots of files, we can exhaust all the request objects, so now need overflow buffers and free lists. And honestly, the improvements are minimal. The bottleneck now is really IO uring itself. I think IO uring might be the wrong tool for this. We have so many requests in flight, we easily exhaust the queue and then have to have loads of overflow and fallback handling. Any efficiency we're gaining is possibly swallowed by just the overhead of IO uring. Let's do something radical. Let's scrap all this IO uring chuff and go back to a simpler architecture. We want a single shared queue for discovered directories. Every thread then follows the same process. Pop the next directory from the queue, enumerate it, push any new directories to the queue for other threads, and then process all the discovered files sequentially. This should keep each thread busy with minimal contention on the locks. The nice thing about this is that as each thread now works on a file at a time, we can bring back the pipeline architecture. And this brings us a pretty good boost to performance, as well as making the code simpler. We now have sub 2-second execution. We can also add a new transform to the pipeline that batches up writes and only actually writes them after a certain size threshold is hit. This lowers the contention on the write lock and reduces the number of write syscalls we have to make. I then played around with various small tweaks to vector scan and the compiler flags, but honestly these made minor improvements, nothing major. There's no secret make it super fast flag I've missed. So our final runtime is 1.2 seconds for 4 GB of data, which I'm pretty pleased with. We could try a different regex engine like Google's RE2, but it is slower. So for off-the-shelf solutions, vector scan is probably about as good as it gets. The final thing is for us to see how it stacks up against Grep, the modern Rust alternative to Grep. And for this specific example, we're within 80 milliseconds. On the losing side of 80 milliseconds, but still very close. Should you abandon Grep for my tool? Absolutely not. Grep is fully featured and battle tested, and all I've done is match it almost in one very specific test case. Again, the point of this was to explore how to do incremental performance profiling and improvements. But hopefully this highlights the difficulties of optimizing modern programs. I made a lot of assumptions during this that turned out to be wrong when actually measured. However, if you enjoyed this and want to see how I fix a 25-year-old bug by John Carmack, then check out this next video.